The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Wassim Ghannoum. He is an assistant professor at basically UT Austin, right? And he's going to be talking about nonlinear modeling parameters and acceptance criteria for concrete columns.
Thank you, Jeff. So what we'll be talking about is some updates we're working on within ACI 369 to update the provisions that are in ASCE 41 and that will be in our ACI 369 standard. So as was mentioned by Bob Pekelnicki, we have this new relationship now where ACI 369 will be handling the concrete provisions of ASCE 41 and we'll be working together to update them. This is brand new, so we've just started. We are just starting to build that standard. And of course, a lot of these presentations that you'll be hearing are actually work that will feed into those technical changes. So what I'm going to talk about is modeling parameters for columns and a bit broader in terms of how do we select modeling parameters and acceptance criteria, how they're currently done, and maybe a way forward to address some limitations. So the background, so ASCE SCI 4113 now, the version will be out soon, prescribes nonlinear modeling parameters and acceptance criteria for various structural components, so columns, beams, joints, and walls. For columns, the modeling parameters and acceptance criteria are given as plastic rotations. So these are plastic rotations for a column, so represented here will give you a plastic rotation or an angle if you want, which is a limiting deformation. The modeling parameters themselves, for those of you that are not familiar with the work of ASCE 41, are what define the backbone curve for a particular element. So if you take, let's say, a column and you push it sideways, you have the elastic portion, then it yields, you get the inelastic portion, and at a certain point you're going to get loss of lateral strength. And the modeling parameter A defines that deformation, the plastic rotation, at loss of lateral strength. And the modeling parameter B will define the end of life of the column, which is the axial collapse of the column. So within the document, these modeling parameters are given for concrete columns, and the acceptance criteria will provide the deformation limits that are acceptable. So you take the modeling parameters, you build your model for all of your components, you run your nonlinear dynamic analysis, or they can also be used for elastic analysis using M factors. It's a slightly different topic, but the same concept applies. And you get your maximum response. And is that acceptable? And this is what the acceptance criteria are there for. Depending on your performance objective, it'll give you a limit on the deformation that is acceptable. If you want to be in immediate occupancy, you have a very strict limit. Obviously, if you want to be at collapse prevention, you're allowed to go very close to the B value all the way out. So, and as I mentioned, all these modeling parameters and acceptance criteria are given in tables, and we'll see them here. So this is what it looks like, what I just described there. Basic backbone curve. If you define A, B, and actually C, the residual strength are modeling parameters. And your acceptance criteria for immediate occupancy will be somewhere around here, life safety, and collapse prevention somewhere out there. So the motivation for what I'm presenting here stems from a little bit how the current modeling parameters and acceptance criteria are defined in the code. So as Robert Pekelnicki mentioned, the modeling parameters are defined now currently conservatively in the code. And so what happens is you have different levels of conservatism for different elements. So say you take a column and an associate in a joint that's attached to it, and you're modeling the behavior. You can get one element, say, is modeled at the mean or median value for the modeling parameters, and another component that is modeled at some level of conservatism. What happens is now, if some models are here, some elements are modeled here, some elements are modeled here, you have varying levels of conservatism across the document. And when you analyze your structure using these backbone curves, you are getting some altered behavior that is not the expected behavior. Now, acceptance criteria, as I mentioned, are selected as fractions of modeling parameters. If you take this is part of the table in ASCE 4113 for columns, looking at, let's say, the A value, so 3.5% plastic rotation, 6% plastic rotation for a B parameter. Life safety will put you at 75% of the B parameter, and collapse prevention will put you at the B parameter here. So they're defined as these fractions of those modeling parameters. So where is the issue here? Let's say you have member 1 modeled at the median value, member 2 modeled at some conservative value. You define your acceptance criteria as 75% of that modeling parameter. So now you have 75% of this value here, and then you have 75% of that value there. And when you look at the probability of exceedance, so when you're looking at acceptance criteria for this member, you have this probability of exceedance of the actual threshold damage or deformation level, whereas this one has a very different probability of exceedance. And so part of this work I'm going to show here is to try to rein in this so that all the modeling parameters are defined at the median value so that we get an expected performance, and then we lump all the conservatism in the acceptance criteria themselves and try to make it uniform across the document so that we are getting some uniform probability of exceedance of whatever threshold value we determine. So the objectives here, as I mentioned, so reevaluate the modeling parameters to achieve median estimates. There's a new database that I developed at the University of Texas, adding to the peer database. We're up to over actually 500 columns at this point. The work I'll be showing will treat circular columns, and the previous version, or the current version of ACA 41, only rectangular columns were treated. Circular columns actually do show quite a bit better performance, probably about 30% or so better deformation capacity, so they're treated separately. We explored these cyclic damage effects, so effects of number of cycles. I'll talk about it a bit. And finally, adjusting the acceptance criteria based on the new modeling parameters that are defined at the median value, and incorporate that conservatism in the acceptance criteria. And I'll talk a bit about this a bit later. Select acceptance criteria as percentiles of modeling parameters, not percentages, which makes a difference. So this is the database. It's available on the NICE Hub website, over 500 column tests. So if you go to these websites here, on the NICE Hub website, you can look for it, ACI 369 column database. There's one for circular columns and one for rectangular columns. The data splits out this way, so I'm going to give you an idea of what the data looks like. If you look at axial load ratio, so this is axial load divided by gross area times F prime C. We have anywhere between 0 and all the way up to about 0.85. Very good spread of axial load ratios, so we cover a wide range of axial load ratios for the columns. Transverse reinforcement spacing to depth. Most of the tests are within D over 2, so the reinforcement is tighter than D over 2, but there's quite a bit between D over 2 and D, and a few that are spaced beyond D. The transverse reinforcement ratio, we go all the way up to about 2%. Transverse reinforcement ratio. A lot of columns at the low end of the transverse reinforcement ratio. And finally, the Vy over V naught term, which determines whether a column is going to fail in shear or in flexure. I put in this little sketch here to explain it. If you take Vy, the yield strength of a column. And if you consider a case where Vy is smaller than V0, which is the shear capacity of the section, you will expect to have a flexural failure and larger deformations at failure. If, however, your Vy is bigger than your V0, that means, or if you want to look at it differently, your shear strength is lower than your yield strength, you would expect to get a shear failure and lower deformations. And we have a wide range of that Vy over V0. Values above 1 mean shear critical columns. So this is where Vy is bigger than V0. This is this case here. And the more ductile modes of failure, flexural failure modes, are down here. Let's talk a bit about that data set in detail. What did we have to work with? For the database, the vast majority of columns, we have only a force deformation plot. So we have lateral force versus deformation of the column, from which we need to extract plastic rotations for the code. So to get the plastic rotations modeling parameter A and modeling parameter B, we first need to estimate what is the yield strength, or the yield deformation of the section. The way we did it was fairly empirically, so we get as good an estimate as possible for the yield drift. So we just ran a secant line at 70% of Vmax and drew down the line here and called this delta Y, from which now we looked at the A parameter was the drift at which the lateral strength degraded by 20% or was at 80% of the maximum minus delta Y over L, and the B term was the drift at axial collapse minus delta Y over L. Not all tests were tested to collapse, so we only have a small subset of column tests that were tested to collapse. Now the most influential parameters we found, looking at a lot of parameters in the database, were the axial load ratio. Higher axial loads will affect the deformation capacity, the transverse reinforcement ratio, and the Vy over V0 term. And these plots here show a little bit. If you look at the Vy over V0 term is by far the most predictive of all of these terms. As you get above 1, you're starting to get into shear failures. Your deformation capacity, so the plastic rotation at failure, drops very, very low. As you go lower to more ductile sections, you see that you get a lot bigger deformation capacity. Same thing for axial load ratio up here and transverse reinforcement ratio. I'm not going to go to these today. These are somewhat important parameters, but in the end we're looking for a simple model, so we didn't want to put 8 or 9 parameters into it. We limited to the 3 most influential terms. Now, how did we calculate Vy over V0? We chose Vy as the yield, the shear associated with the yield strength of the member. We did not use Vp in this study, as is currently in the code, which utilizes 1.25 Fy. The reason for it is a lot of the columns we're looking at have low ductilities. These are existing columns, shear critical columns. They are columns that cannot get to such large ductilities where they will get to 1.25 Fy. So we selected to just use basic yield strength. And the V0 equation is the shear strength equation available currently in the code. We did a minor change to it with the phi factor here to account for very wide spacing of transverse hoops. If the S over D ratio is greater than 1, in this equation you will neglect the effect of the shear reinforcement. If they're spaced too far apart, you're going to get a shear crack that will not intersect anything, and so you just neglect the effect. If your spacing to depth ratio is smaller than 0.75, you will use the full capacity and you linearly interpolate between the two. Another thing about the parameters is something to consider is the current version of the code is looking at ranges. You're interpolating between ranges of axial load of 0.1 to 0.6 and transverse reinforcement ratio of 0.6% to 0.2%. And if I draw axial load ratio versus transverse reinforcement ratio, you're actually interpolating in this dark square. And anything outside of this dark square becomes constant. And so in this next iteration, we're considering a much bigger area for interpolation, so you're capturing the effects of the data outside of this range. And this is the final version for the A parameter. We ran some regression analyses and got an equation for rectangular columns and one for circular columns. Starts off here at 4%. Axial load ratio is negative sign. The higher the axial load ratio, the lower the deformation capacity. Transverse reinforcement ratio, the more you provide confinement, the better you are. You increase your deformation capacity. And Vy over V naught, as you get to a larger number, get a shear failure, closer to shear failure modes, you get a lower number. And same thing for circular columns, but what we saw for circular columns that are spirally reinforced is that these values are, if you look at the maximum value that these equations will allow, you have 4.8% for rectangular columns and you have 7.1% for circular columns. So they're doing a fair bit better than the rectangular columns. Now if you look at analysis of fit, current ASCE 4106, which is also the ASCE 4113, you look at the error between experiment and estimate and the cumulative distribution. You expect half of your data points to be on the left of zero error and half to be on the right if you're actually targeting a median value, which is what we get. This is the blue curve here. It runs in at 0.5 at zero error, so half the data points have a negative error, half the data points have a positive error. The current ASCE 41 estimate was aiming a bit on the lower side at about 35%, 35th percentile. For circular columns, on the other hand, since the current code standard does not treat circular columns, it is very conservative. You see that it is actually getting something on the order of 25th percentile on the value, whereas now we pushed it much closer to the 50th percentile and reduced the scatter a little bit in that data. Taking it even deeper, this is the overall. Are we getting the mean value, the median value, and the overall database? We are. Are we getting the overall median value at different within the multi-dimensional parameter space? Are we getting a median value everywhere, or are we just overly conservative on one side and not conservative on the other side? And when we plot these data for different parameters, different ranges, we find that the curve does actually run across 0.5 and 0. We are getting, for the most part, a median estimate over the entire parameter range. So that gives us confidence that over the entire parameter range we have what we're looking for. Same thing for circular columns. And then we're looking at things, so also we're going to test it for other parameters that are not in there to see their effect. One thing is I was worried about, well, transverse reinforcement ratio is important, but also spacing. Do our equations give us any bias with respect to spacing of the hoops? And when we plot the error versus S over D, we see that it is overall for rectangular and circular columns, there is no bias also for the spacing over depth ratio. And then we looked at the hooks, and so will 90-degree hooks make a difference? And it turns out, if you look at all the black spots here, they're roughly distributed, and here they're actually a bit conservative on the so anything above the line is a conservative estimate for the larger S over D ratios. And I dug into it, like, well, you know, we all would like to think that 90-degree hooks will perform worse, but it turns out that the test data that we have, the 90-degree hooks are the ones that are spaced. First, a lot of them are spaced far out here, and the reinforcement ratio is very, very low when you have 90-degree hooks typically. And so the low reinforcement ratio means that the contribution of these ties is very low to begin with. So we don't see any trend when we look at the hook angle. And most structures out there are like this. Most structures will have 90-degree hooks will have very little reinforcement ratio. If you start putting a lot of reinforcement in your section, you will be going to 135-degree hooks. So the equations work as long as you don't have the odd case of 90-degree hooks that are spaced very, very tight, which I don't know of any building that's built it. Next, I'd like to talk about the B parameter. Because we have very little data, we were not comfortable using regression models for it. So what we did is we got a Elwood-Maley model, simplified it a little bit for axial failure, and looked at if we can extend that model to get a good estimate of axial load. And if we looked at the current ASCE 41 values here versus the measured axial values, currently this is a subset of the data of columns that failed axially, we find that the measured numbers are bigger than what ASCE 41 predicts. the values are conservative. So the drift or the deformation at axial collapse is conservative currently. If we use the simplified model, we get a much better fit except for a few points. These points are very unconservative, but these points are columns that were tested to very demanding loading protocols, bidirectional loading, 3 loading cycles per at each increment, or 6 loading cycles at each deformation increment. And so here we start seeing the effect of loading cycle. As we cycle a column more and more, it'll accumulate damage and get a smaller deformation capacity. So if we apply a factor of 0.5 to the model drift at axial collapse to those columns that were loaded at 6 loading cycles or biaxially, we find that the data actually fits really, really well. Now let's look at this. This is a subset from a project that my co-author Adolfo Matamoros worked on. If we go back and look at what happens in the big database we have, ignoring that 0.5 factor because most columns tested here, I think all of them are uniaxial and had only 3 loading cycles per drift level, and we look at the points in black are the columns that actually failed, were pushed to axial failure. The other ones are columns that were not pushed to axial failure. We find that the model does a pretty good job at capturing that effect, capturing the deformation at axial collapse for these columns. And for circular columns, it is a little bit on the conservative side, but we only have 9 data points. So we did not see any warrant to increase the numbers. We see that it seems the circular columns also perform better at axial collapse than rectangular columns, but given only 9 data points, we did not want to push it beyond this. Now if we look at ASCE 41 versus the proposed modeling parameters, this is the rectangular column A parameter, circular column A parameter. We see a little bit of a shift for the rectangular columns, but a very large shift actually for the circular columns that were treated very conservatively in the current code and are now treated to the median values with the proposed equations. Looking at modeling parameters B, all of them have shifted significantly. The current code is conservative. We are targeting something that is much closer to the median value now with the current proposed equations. And finally, last little bit, I'm almost out of time, or maybe I am already out of time. Acceptance criteria. So looking at defining acceptance criteria, instead of a percentage of the modeling parameters as I talked about, a percentile. So if you try to look at, I'm just going to take a quick example here. Life safety for primary element, 20th percentile of modeling parameter A. So if I want to have a 80% confidence that I will not exceed A, the point of lateral strength degradation, I need to take 50% of the equation, the rectangular column equation. However, for a circular column, because the spread of the data is different, to get the same 20th percentile, I need to select 30% of my parameter A. And there is a significant difference. So if we're going to move to probabilistic definition in the next version of the code, we should be looking at percentiles and then back calculating what that percentage difference is to get the same level of conservatism. And I'm not sure I have time for all this, but summary, modeling parameters are at the median value. We developed new relations for modeling parameters A and B. Circular columns are treated differently because they perform much better. Modeling parameter A defined through regression models, B through a behavioral model because we don't have a lot of data, and the acceptance criteria defined as a percentile. Thank you.